Welcome everyone. It's our great pleasure to have Dr. Goyal today for our first seminar in this semester. It's joined with IEEE SB local seminar. So Dr. Goyal received his Ph.D. from Berkeley with award, and then he also was a member of technical staff at Bell Laboratory and also senior researcher for Digital Foundation, and also the Eastern and Harvard E. Erdogan Associate Professor at the MIT. Now Dr. Goyal is Associate Professor at Boston University. Dr. Goyal received numerous rewards, including many best paper and at a very prestigious kind of top-tier conference. And Dr. Goyal is right now is also a fellow at IEEE. And yeah, I think I don't have time to list all the awards Dr. Goyal received, so I will just leave the floor to Dr. Goyal. So let's welcome our speaker.
Thank you. This is not a smooth way to start a talk, but I forgot to ask when I should stop. Is it an hour including questions or not including questions, or how should I?
I think usually we have 15 minutes for talk, then
okay.
10 to 15 minutes for questions.
All right, very good, very good. All right, well, thanks very much for the introduction. I'm glad you didn't try to say more, make it more awkward and embarrassing. I'm really happy to be here and share with you work that my students and collaborators and I have been doing over the last several years, focused on developing methods for high photon efficiency in active imaging. So today I'm going to give you an overview of that line of work, and I want to emphasize the simplicity of the modeling that leads to the results that we obtain. And so through that, I hope to show you that imaging is possible with very small number of detected photons. And I'll shift to include more recent results in helium ion microscopy. The methods are really applicable to any focused ion or electron beam microscopy. So in that, I'll try to show you that imaging is possible with a very small number of detected electrons. So that's what I hope to convey through the modeling and methods. Now, if this talk were 2 to 3 weeks later, then I would include work by NC State graduate Yanting Ma. She's been doing brilliant work in my group. So I want you to know that there's precedent for a pipeline from NC State to BU. And I'm looking for postdocs and Ph.D. students, so let me know if you're interested. All right, so the main topic for the day is reflectivity and depth imaging from single photon detection data in challenging settings. And here what I've done is I've gathered some examples where in the first row we have the results of some kind of conventional data processing, and in the second row we have the results of our data processing with the same input data. Now the first column shows what we call first-photon imaging. In first-photon imaging, we form these reflectivity and depth images from a single detected photon per pixel location, and it's challenging not just because of a small number of detected photons, but also with approximately equal power for signal and ambient light. So I've labeled that column with half a signal photon per pixel and half an ambient photon per pixel, but we're able to generate those results. And that was the, that was the root of this line of work. And since then, we've subsequently looked at other settings with their own complexities. So the second column shows work where instead of using a raster scanning system, we have an array detector. Array detectors bring their challenges with coarser time resolution, and we obtain the results in the second column when we introduce some new methods to deal with that coarser time resolution. The third column shows results that we obtain without assuming any transverse spatial correlations. There, because we're not assuming those correlations, we do need a larger number of signal photons to obtain good results. But again, by introducing new signal processing, we can do better than with conventional techniques. And then the last column shows some work where scenes have multiple reflecting layers per transverse location, and we're able to estimate multiple depths per pixel through a partially transmissive scatterer. Even more recent work in this direction is about withstanding large amounts of background light. So here I have in the top row photon detection events mapped to 3D positions, but in that top row, as I rotate around those point clouds, I mean, it looks terrible because the ratio of ambient detection events to signal photon events is very high, or it's low signal to background ratio, and then the bottom row shows the results that we obtain after doing a reasonably good job of guessing which photon detections are due to signal and which are due to background light. So I want to jump into the very basic ideas behind these methods, and in the latter part of the talk, I'll shift to work that has different goals in microscopy instead of depth and reflectivity imaging. So the central ideas are very simple. I'll start with a review of the basic ideas around active imaging with pulsed illumination, and then how you do the modeling at a photon by photon level to get an inverse problem that can be solved to give the results that I've shown. All right, so we're in a conventional sort of active optical imaging setup with pulsed illumination, so a LIDAR type of system. LIDAR systems are of increasing importance these days because of their use in autonomous driving. So there's actually a lot of activity in the LIDAR space commercially with a lot of new hardware systems being developed, a lot of those companies that develop those LIDAR systems being acquired by auto manufacturers. So it's a very active area. Now, basically, when you illuminate a patch of a scene with a pulse of light, there are several properties that can be inferred from the relationship between the transmitted pulse and the received pulse. So the time shift is called the time of flight, and it reveals the distance of that scene patch because the speed of light is finite. The baseline offset in that received waveform, that tells you how much ambient illumination there is. And the amplitude of the reflected pulse, the received pulse, over the background gives you the reflectivity of the particular scene patch that you've aimed your laser at. Then, if you scan that laser source over your whole scene, you're able to form a reflectivity image and a depth image pixel by pixel. So that's what a raster scan LIDAR system does. So that's conceptual without any regard for how the illumination and detection devices work. Now, to have a photon efficient system, so that is to make the most of every detected photon, we want to use a single photon detector. All right, so throughout this talk, throughout the rest of this talk, it's really a conceptual talk. But I'm going to be giving you experimental results while I talk about the concepts. So in the experimental results that I'll show you, we've used a 640 nanometer laser diode as the source. It has 226 picoseconds RMS duration, 10 megahertz repetition rate, 0.6 milliwatts average power. Right, so we've done proof of concept experiments to back up the theoretical developments that I'm discussing here. Now, with that light source, we raster scan over the scene, and we do the light detection with a single photon sensitive detector. So in particular, we use this microphoton devices detector, which has a particular quantum efficiency, a particular sensor area. Now, we need to be able to record the detection times of the photons relative to the pulse emission time, and so that's done with a time correlated single photon counting module, and we used in particular something from PicoQuant set to have time bin durations of 8 picoseconds. All right, so you could consider that's all trivia. The particular hardware details of our implementation is kind of trivia, but we're going to raster scan that light source and do LIDAR imaging in the way I've described, using the time shift to reveal distance, etc. Now, an unstated assumption in most of the work that uses single photon detection in LIDAR is that you're going to form a histogram of the detection times, and that histogram, collected over many, many repetitions of the laser, is a proxy for the analog waveforms that I showed you on the previous slide. Now, it's a discrete time proxy because there's a finite time bin resolution that here happens to be 8 picoseconds. It's also a noisy proxy for that analog waveform because the number of photon detections has randomness to it. But still, it's treated as a proxy. Now, we're trying to get by with extremely low numbers of photon detections. So the idea of forming a histogram starts to feel a little bit silly if you have only 1 or 2 events. You'd never form a histogram with only n equals 2. It feels silly. It's not unreasonable to get by with such a small number of photons when you do your modeling at the photon by photon level and you don't try to form a histogram. So let's look at what I mean by that photon by photon modeling. So this time correlated detection of the individual photons, it puts the detection on the same time axis as the illumination. And if we had only backscattered light from the scene, then what we should be seeing at the detector are arrivals in an inhomogeneous Poisson process, where the rate function of that Poisson process, which is shown in orange here, is a scaled and shifted version of the illumination waveform. There's also some ambient light. The ambient light has no preferred times, right? So the ambient light detections are a homogeneous Poisson process, and the detection events due to signal and due to ambient light, they're no different to the detector. So what we really observe is the sum of those two rate functions as shown in yellow here. So what we get to observe are arrivals in an inhomogeneous Poisson process with a rate function that looks something like that, actually, or a periodized version of that, because we keep repeating over many, many laser pulses. Now, the first illumination period might not have any detections. The second illumination period might not have any detections. And then let's say in the third illumination period, there's a detection. So what I've marked here is a detection happening at a relatively likely time. It's relatively likely because I've marked it as happening where the yellow rate function is high. But a detection could be at a relatively unlikely time. In that case, that detection is due to ambient light instead of back reflected signal. And these photons are not colored orange and blue, right? We can't tell them apart. We don't know that yellow function. What we're trying to figure out is the time shift of that yellow function. Okay. So let's suppose that we have a strategy of sending laser pulses towards a scene patch until we detect one photon. Right, so this is the acquisition protocol for what we call first-photon imaging. Now, now that I've mathematized everything, you can see very simple probabilistic models for what we observe. Right? So we've decided that we're going to send these laser pulses until we get one detection. There are two, I can describe the time of that detection with two random variables. Basically, I look at the detection time modulo the repetition period of the laser, and I call Kij the number of pulses emitted. Here, Ij is the pixel index. So K is the number of pulses emitted until I got that first detection. And then T is the detection time relative to the most recent pulse emission. It's the detection time modulo the repetition period. So it turns out that K essentially encodes the reflectivity of the scene patch. And what I mean by encodes it has a distribution that depends on the reflectivity alpha Ij of scene patch Ij that I'd like to be able to estimate. Right? So with this protocol of pulsing until we get a detection, it's like flipping coins until we get heads. You get a geometrically distributed random variable with the parameter of that geometric distribution being related to alpha. The Tij, that is related to a depth through the speed of light, as always in LIDAR. But the distribution of Tij is a normalized version of the function that I've been showing you in yellow. It's a normalized version of the pulse plus background distribution. Now, the negative log likelihood of a geometric distribution is convex. With this relationship between P and alpha Ij, we have that the negative log likelihood of Kij is convex in alpha, and that there's no dependence on Z, the depth. But unfortunately, when we have background present, the negative log likelihood of the Tij is far from being convex in Z. It's only convex if there's no background and we make an approximation like calling the pulse-shaped Gaussian. Okay, so I've written out these mathematical relations because they suggested to us an approach to forming images from this data. So this is not a statistically optimal way of jointly estimating these variables, but it suggests to us a simple separation. So first of all, we have that we can estimate the reflectivity image alpha from just the Kij data, and because of this convenient property that nature has given us with the convexity, we can easily do a regularized maximum likelihood estimate with by solving a convex optimization. And that's the first step of our method. Then we wish that we could do a regularized maximum likelihood estimation for the depth, but the lack of convexity makes that an unattractive thing to do. So we would like to be able to make believe that there's no background light. So we introduce a step where we try to guess which detections are due to signal and which are due to background, and censor the noise. If we've done that reasonably well, we can make believe that there's no background light and have a convex optimization problem to solve to estimate the depth image. And so let me show you the results that we get from this. So this is data collected for a mannequin wearing a black t-shirt with some geeky text on it, which will come through once we do proper higher quality image formation than this. So this is essentially our raw data, but what we've done is we've taken the Kij values, the number of pulses we need until we detect a photon, and mapped it to an initial reflectivity estimate. So all of our data is a 3D point cloud, and we can overlay reflectivity on positions. Now, in the first step, we want to do regularized maximum likelihood estimation. Like I said, nature is kind to us in the fact that we have the negative log likelihood being convex, so we can regularize in some way. And I don't even want to concentrate on really comparing different ways of regularizing. But basically, we want to exploit piecewise smoothness of the reflectivity. And these are the results that we get. So this shows this highly improved reflectivity estimate, still overlaid on a very noisy point cloud because we haven't done anything to improve the way that the depth is estimated. But you can see, especially in the straight-on view, that it's an extremely improved estimate. Now, we'd like to have some way to guess which photon detections are due to light back reflected from the scene and which ones are due to ambient light. We have a heuristic for that based on what's called a rank-ordered absolute difference statistic. So we compare a pixel's Tij value to the values of neighbors, and roughly speaking, if the differences with several neighbors are small, then it's likely that at that pixel you have a detection due to signal. If the difference is large, then it's less likely that the detection is due to signal because conditioned on being a signal detection, the variance is very low. Conditioned on being a noise detection, the variance of the Tij is large. It's based on the entire pulse repetition period of the laser. So this is one heuristic that we use for guessing which detections are due to signal and which are due to noise. And after we censor the detections that we think are due to noise, we end up with this result at stage 2. You can see that a lot of the detections due to noise have been removed, but certainly not all of them. And this method does not perform particularly well in the very dark parts of the scene. Of course, it's hard to perform well in the dark parts of the scene. Not much light reflects back from a black t-shirt. And it also performs worse near the boundaries, and that's also as to be expected. But that turns out to be good enough for our purposes because we then make believe that there's no ambient light and solve a convex optimization problem for the depth, where we form an analytical approximation for the pulse shape that has a negative log that is convex, so that this is a convex optimization problem that's easy to solve. And then this becomes the final reconstruction. So this 3D reconstruction of reflectivity and depth is being formed from only half a signal photon per pixel with also half a ambient light detection per pixel. So we can again compare what we started with the final reconstruction. And this is coming from doing this really photon by photon modeling instead of thinking of the received data as a proxy for an analog function. All right, and we can evaluate the error that we achieve by repeating this over many data collections. This shows that we're getting sub-pulse width resolution. So if you took the pulse width and appropriately scaled it, you'd get 4 centimeters. And here you can see that, say, on the face, the mean absolute error is less than that resolution suggested by the pulse width. Now, I don't want to make believe that there's too much magic here. I mean, there's no way we could get this kind of sub-pulse width resolution if we weren't assuming that what we see in the world has this piecewise smoothness to it, and that the piecewise smoothness really exists. But it's really a very, very weak signal that's allowing us to get this kind of sub-pulse width resolution. All right. Now, there are at least a couple of weaknesses in this as an approach. I mean, really, this is, I'd like you to think of this as conceptual. It's a demonstration that you can get by with extremely weak signals. It's not that I think people should go out and build LIDAR systems that detect so few photons and then drive their autonomous cars around based on so few detected photons, right? That's ridiculous. But it's a proof of concept of what you can get away with in terms of the signal being weak. Now, here, one weakness is that acquisition by raster scanning might be too slow, and so you'd rather use an array of single-photon detectors, and we did some work along those lines. And you could also say that this is a crazy thought experiment. It's a crazy thought experiment to say that my raster scanning with some Galvo system is driven by whether I've detected a photon or not, right? Because the photon detections are happening so fast, it's difficult and problematic to implement the random dwell time that's suggested by this. Well, it turns out that the randomness of the dwell time probably has little to nothing to do with why we were able to obtain performance that's so good. So, you know, even though it's kind of catchy to say I've detected only exactly 1 photon per pixel, well, instead, I could use deterministic dwell times at very low signal rates and see what I get. So let's now change our acquisition protocol to having some deterministic number, capital N, illumination pulses at each pixel ij. Then, you know, so far this is about undergrad probability, right? And it's just as easy as an undergrad probability problem. Now we have more detection times, a random number of them per ij. And instead of a geometric random variable, we have a binomial random variable where p is related to alpha in the same way. The times modulo repetition period have exactly the same meaning and the same distribution. And nature is exactly as kind to us as it was before, because the binomial distribution has this convenient convexity of the negative log, but the distribution of the Tij times does not have that convenient property unless there's no background light. So we developed a similar method. We again apply some regularized maximum likelihood estimation for the reflectivity, developed a slightly different method for censoring the noise, and then do regularized maximum likelihood estimation of the depth. And here are some sample results. So, well, what I happen to be showing you is not all the way down to 1 photon per pixel, but it's, let's say, 2 photons per pixel. And our results are in the last column, and you can see that compared to conventional interpretation of the data combined with state-of-the-art denoising, we perform much, much better. Right? So without getting into the details too much here, you know, the 3rd and 4th columns are like conventional image formation combined with not stupid methods for denoising. You know, they are actually methods that we modified to fit this situation as well as we could, but they still don't perform as well as the style of photon by photon modeling that we developed. And in particular, like if you look at the depth image root mean squared error, it's like a factor of 20 improvement from exactly the same data. All right. Now, another twist in the story, and really the last one that I'll talk about in significant detail, is what if we want to be able to withstand a lot more background light? So we approach this question in the setting of deterministic dwell times, and our method is based on doing a lot better job at that second step. That second step where we try to guess which detection events are due to back-reflected light and which detection events are due to ambient light. All right, so what we do is we think of it as having a hypothesis testing problem at every pixel. So for that reason, we called it Neiman-Pearson censoring. We say you're going to see some largest cluster of detection events. Right? The detection events randomly, some cluster will be the largest cluster, and normally, whatever that largest cluster is, you would decide, well, I'm going to guess that that corresponds to the true depth of the scene patch. Right? That approach is fine when you have enough signal photons detected. But when you try to push these kinds of systems to having very, very weak signals, you're very often wrong. That largest cluster occurs at the wrong depth. So we wanted to have a rule for deciding whether that largest cluster is reliable enough to use it, or whether you should throw away all the data from that pixel. Or at least, we don't really throw it all away, but for 0th order, to think of throwing away all that data. So we set a threshold for the probability of falsely accepting a cluster of photon detections as being due to signal. And so it turns out that you can compute a mapping between the probability of being wrong that you will accept, you will withstand, to the number of photons that you should see in that largest cluster. When the best cluster has too few detections, you're better off erasing the data at that pixel location and instead in-painting it from neighboring pixels. On top of that idea, we actually layer something else. So instead of literally throwing away the data when it seems like the largest cluster doesn't have enough photon detections to be reliably indicating the depth, we merge pixels that have similar estimated reflectivity to form superpixels, and then within a superpixel, the n-min goes up, but we may have enough detections to more reliably guess which photons are due to signal and which are due to noise. And this approach allows us to withstand a lot more ambient light. And so what I'll show here is simulated results when there's 25 times as much ambient light as there is signal. So if you look at the second column really indicates you just how weak this signal is. So the raw photon counts per pixel are extremely dominated by the background level and the Poisson noise, the Poisson variation of the background noise. So you can barely make out anything here. If you had an oracle that told you which detections were due to signal and which were due to noise, you just throw away all the ones that are due to noise and form an image. It wouldn't be perfect, right? Because there still would be some randomness in the detections due to the Poisson variations of the signal component. But we're able to get somewhat close to having a signal oracle and really much better than the best existing method, which was our own previous method. So you can actually withstand a lot of ambient light when you use the detection times effectively to guess which photons are due to signal and which are due to noise. All right, and we can get similar improvements for more complicated scenes. All right, so what I've concentrated on here are results from the first 3 papers. The first 2 had work that was focused on getting by with very few detected photons, and then the third was where we've extended that to handle a lot of ambient light. There are other subsequent works, like one in which we don't rely on any transverse spatial correlations and still obtain similar improvements. I'll show you images from another where we estimate multiple layers in a scene. So here we again have a raster scan LIDAR sort of setup, but now a mannequin with a different geeky t-shirt behind a partially reflective scattering material. And by doing this photon by photon modeling, we're able to much more accurately estimate multiple depths per pixel. This is definitely harder to interpret because there are multiple depths per pixel. So for this scene, in the side view, you should see a layer that's the mannequin that's separated from everything else. And so that's what you see in the bottom with our method. But with a conventional method of Gaussian, mixture of Gaussians fitting approach, you can tell that the result is bad because you don't see a mannequin separated from the background. Similarly, you can have something like a synthetic sunflower that we worked with, and again, you can see that we've obtained a much better reconstruction because that sunflower is separated well from the background. All right, so I think it's a good place to pause before shifting into a somewhat different topic for just about the last 10 minutes. So does anybody have any questions about the work at this point? Please.
How would you compare what you're doing with Eric Poisson's earlier papers in this general area?
So I'm familiar with Eric Fossum's work on, I forgot his terminology. I mean, the JOT-based.
Yeah. He calls it the QIS.
QIS, yeah, quantum image sensor. All right, so those works are not focused on having high time resolution. So you can't, I don't think you can do depth imaging with the type of QIS devices that Eric Fossum's group has been developing. If you look only at the reflectivity reconstruction, then there are some interesting overlaps. I don't really know how to compare and contrast them. I mean, I'm familiar with that line of work a bit. With the QIS sensor, you don't really have the ability to count all the photons. You definitely don't have the ability to time tag them, but you don't have the ability to count all the photons. And I think that the signal processing questions that arise are more around where to set threshold levels in the sensors so that so that you distinguish between what you quantize to 0 and what you quantize to 1, and then to be able to form images from that. I think I should leave that to more offline discussion, because I don't think there's any algorithmic part that I can compare to anything they've done, and the sensors don't have time resolution. All right, well, in fact, that's a perfect question to lead into the other topic of the day. I want to share with you even more recent work in helium-ion microscopy, and I say it connects very well because what we are proposing, to give you a preview, is to introduce time resolution into focused ion beam microscopy, even though nothing that you're trying to estimate depends on a time of flight or on time at all. The introduction of the time resolution is entirely to mitigate the noise, or to mitigate one component of the noise. So when I showed you that we could withstand 25 times as much ambient light, we get a much better reflectivity image than you could get without the time resolution. I'm going to show you something a little bit similar here, where the time resolution, again, it does not itself relate directly to any physical quantity we're trying to estimate, but the time resolution lets us form better images. All right, so a helium-ion microscope, it's got an ion source and a secondary electron detector, and what you do is you alternate between imaging with helium ions, like having an incident helium ion beam, and neutralizing the surface charge, because you have a charge buildup from the ions, so neutralizing the surface charge. Now, we're going to concern ourselves only with the imaging parts, and we're going to quickly get to some mathematical abstraction so that we get away from the physics. Now, in this instrument, You're again imaging by raster scanning, like in most of the LIDAR topics that I talked about. So the beam is raster scanned with some kind of fixed dwell time per pixel, and as the beam is raster scanned, the detected secondary electrons, these are electrons that are dislodged from the surface or emitted from the surface because of the incident helium ions, they're detected at the secondary electron detector, and the intensity of the signal at the detector gets mapped to a gray level. The promise of helium ion microscopy is to achieve very high resolution and high surface sensitivity, good depth of focus, to be able to image insulators without metal coatings. So that's to contrast with scanning electron microscopy, where imaging insulators is difficult because of the way the charge buildup occurs on insulators. And the advantages, the high resolution advantage comes from the short wavelength of the helium ion along with the low interaction volume that you have when a helium ion strikes a sample. So what I've shown here are some samples of results from the Salk Institute of imaging some sort of a biological sample. Now, the major limitation of helium ion microscopy is that the helium ion beam is damaging the sample. And that weakness is even greater if the ion beam is of heavier ions. So people do focused ion beam microscopy with heavier ions as well. But helium ions are popular because they're relatively light compared to other ions that could be used. So this just illustrates the damage to a sample that occurs from the imaging process. So you see that starting with 52 seconds of imaging to 364 seconds of imaging, etc., the sample itself is degrading because of the imaging process. So in helium ion microscopy especially, and in other kinds of microscopy as well, it can be very valuable to have a low dose. So on the other hand, of course, increasing the dwell time generally means that you're measuring more useful information from the sample. So there's a balance here, and so we want to be able to make the most out of any fixed dose. If we're able to show that you can do better than people usually do with some fixed dose, that means you can lower the dose and potentially image things that you would not have been able to image before because the sample would have been destroyed by the imaging process itself. All right, so I want to quickly get away from the physics and turn it into math. So we look at the incident helium ions as being a Poisson process. And then for every incident helium ion, there's a burst of secondary electrons that are detected at that secondary electron detector. Now, there's some fixed dwell time that you have per pixel, and so in that fixed dwell time, there's some number of ions, we'll denote it by m, and model it as a Poisson random variable, and there's a number of ions, xi, number of secondary electrons emitted due to ion number I. Okay. Now, for now, at least, let's model each xi as a Poisson random variable as well. So the observation that we get at any particular pixel, y, is the sum of a random number of xi's. So this might be reminiscent of something you saw, again, in an undergrad probability class, random sums of random variables. In any case, the expected value of y is proportional to the beam current lambda and the parameter eta of the Poisson random variable that's describing the number of secondary electrons. Right? So the lambda is just some fixed number. That's a dial position on the instrument itself. So we look at the fact that the expected value of y is proportional to eta as a good thing. It means that any reasonable way to scale y gives an image of the quantity that we care about. Eta is the quantity that we care about because it's telling you a material property and how it varies as you raster scan. So this is setting up the problem. We're really trying to estimate eta at each pixel, and the straw man is to just use any scaling of y as the way to form the image. All right. So since the goal is to estimate eta, that secondary electron yield per ion, y divided by m would mean that you're taking the number of secondary electrons that you've seen and divided by the number of incident ions m. That's a better way to estimate eta than to take y and divide it by lambda, which would mean you're dividing by the mean number of ions. Right? You can use the actual number of ions versus the mean number of ions. Well, it makes more sense to use the actual number of ions, but you don't actually observe m. Right? So this is fundamental to our problem, where the randomness of m is a nuisance to us. We wish that we could be dividing by the actual number of ions, because then we would use secondary electrons per ion as our estimate of eta. All right. So the key idea is to introduce time resolution where there never was time resolution before. We changed the data collection so that we can form a very good guess of the number of incident ions. So we have, again, the same picture of a fixed dwell time, but now we divide the fixed dwell time into sub-acquisitions. And very roughly speaking, if the sub-acquisitions are short enough, the number of ions is really the number of sub-acquisitions in which there was at least one secondary electron. Doing that assumes that there are at least one secondary electron per ion, and we use a better model than that. But just roughly speaking, this gives you an intuition for why adding time resolution into this problem, which really had nothing to do with time, can help us. It can help us mitigate the nuisance randomness of m. So the theoretical analysis that we use to back this up is to compute ratios of Fisher information. And you can think of that as proxy for ratios of mean squared errors that you obtain. So it's like it's a proxy for a mean squared error improvement factor. And we can compute the ratio of Fisher information to see that when we do time resolved sensing, there can be a large improvement factor. So this improvement factor, again, it can translate into lower MSE or lower dose, because MSE and dose are inversely proportional for this kind of imaging. So to show that in some simulations, we use a Shepp-Logan phantom. So we treat this as the ground truth, where it's the modified Shepp-Logan phantom that you get from MATLAB, scaled to 2 to 8. So we're assuming that the blackest pixels here have 2 secondary electrons per incident ion on average, and the brightest pixels here have 8. That's a somewhat reasonable range for helium ion microscopy, and we see an improvement factor of 2.6 in the mean squared error from doing time resolved sensing in a problem where, again, there really was no property that was really related to time. And it's really just the beginning of the story, because assuming that you get to count the number of secondary electrons directly is not the way today's helium ion microscopes work. Instead, the secondary electrons hit a phosphor plate, and what you measure is actually more complicated than a count of the number of secondary electrons. But we can incorporate that into the model with some compound modeling. So I called this Y before, the number of secondary electrons. Maybe we don't get to measure that directly, but instead we measure something with we measure a sum with Y terms in it, for example. And we could call this, say, a Poisson-Poisson-Gaussian model when each secondary electron has a Gaussian contribution to the quantity that you measure. That allows us to do similar analyses and still show that time-resolved sensing makes this form of microscopy considerably more powerful. And we can do simulations with the Poisson-Poisson-Gaussian model instead of the Poisson-Poisson model, and again have improvement factors that are consistent with what the theory tells us. And finally, we've worked with real data provided to us by John Noddy of Zeiss. Zeiss is the main manufacturer of helium-ion microscopes. So Zeiss provided us with some data. Now, I am absolutely, I'm not going to claim to you that the images you see will look dramatically better. I don't want to claim that. But our methods for estimating the mean squared error show that we have achieved a significant improvement. So what John Noddy provided us is data that is divided into sub-acquisitions like we ask for, because we want time-resolved sensing. So we imagine a 0.1 picoamp beam current, 200 nanosecond dwell time per sub-acquisition, and that translates to about 1/8 of an ion per pixel per sub-acquisition. So 1/8 is low enough that you can imagine that every sub-acquisition has either 0 or 1 ion. And for a fixed amount of data collected, we estimate about a 2.7 times reduction in mean squared error. Or to achieve a constant estimated mean squared error, we were able to exhibit a 40% reduction in the dose. So I'll wrap it up here. I showed you two kind of different examples, but kind of related ones, by talking about reflectivity and depth imaging in raster scan LIDAR and this focused ion beam imaging. Both of these classes of examples are really about doing your modeling at the right level that you're able to achieve something interesting, and that particle by particle modeling can be useful. At a finer scale, some of the take-home messages are that when all you care about are certain parameters of a distribution, you should always be trying to estimate those parameters directly instead of assuming that you need enough data to first form a non-parametric density estimate and then do your subsequent processing. That's really what it would be to use histograms in LIDAR as proxies for analog waveforms, is to say, I need enough data to first form a non-parametric density estimate and then do the rest of my work. And then in both the 3D imaging and the helium-ion microscopy, we have that something that's seemingly irrelevant can allow us to mitigate noise. So in helium-ion microscopy, the time resolution is seemingly irrelevant, but it actually mitigates the source shot noise. And in the 3D imaging, timing is seemingly irrelevant for reflectivity, but it allows us to separate signal from background and therefore get significantly improved performance there. All right, so thank you very much, and I'll stop here to take more questions. Dror, please.
Yeah, so I'm wondering, from a very different type of perspective, you've described various algorithms to deal with these optical systems, and I really appreciated how multiple times you kind of mentioned this is heuristic, that's heuristic. Like, I really appreciate your sincerity here. And from a different perspective, have you guys, or maybe other groups, wondered about how from an information theoretic perspective, you have this Poisson channel, or at least it can be modeled as Poisson. How much information is here? Can you have any sense for how close your methods are to optimal?
Okay, so I think that if you're willing to assume that you know the pulse shape well, then I don't know about a capacity point of view, but you can use the tools of like Kramer-Rao bounds to evaluate how close you are to optimal. So,
right, so I'm kind of thinking, and we should probably chat about this offline later this afternoon, but I'm kind of thinking along the lines of, I have a signal, and I'm measuring it through a very complicated channel. What's the capacity of that channel? Based on the capacity and rate distortion limits on trying to describe that signal, how well can I estimate the signal? Yeah, we can definitely.
Yeah, I mean, that's it. I think that's a great direction for further thought, for sure. I'd say we've used tools like Fisher information a lot. We've not really used channel capacity types of tools. Of course, we can pick this up in more discussion later. It reminds me that years ago, I was involved in a project where the program manager was fixated with learning how many bits of information about a scene can you gain per detected photon. That's actually what led us to do the work. The program manager's obsession made us think of doing this work. It's like, well, depth imaging has the potential for gaining lots and lots of bits of information per detected photon, because the number of bits of information is really not dependent on any kind of signal strength or anything like that. It's just dependent on the a priori uncertainty of the depth, right? So it's essentially, an unbounded number of bits per detected photon if there's no background light, et cetera, et cetera. So it led us down this path. But while we were thinking about those kinds of questions, we kept running into the fact that these aren't problems where you really design the input distribution. So it's not, we might find something interesting from channel capacities, or we might find that because you are not designing the input distribution, it's not the right tool. Please.
Yeah, I have two questions. So I'm not very familiar with this Helium, but the first question is for the 3D reconstruction, how efficient is it? How efficient? I mean, how long?
In the computation time.
Yeah, computation time. So the first question. The second question, so I see right now your main method rely on the maximum likelihood, right? It's more like a data driven. So do you think it's possible, for example, since you are doing the image reconstruction, do you think it's possible, for example, to bring some prior knowledge to form, or for example, formulate as a Bayesian estimation problem, such that you can take advantage of the, for example, both spatial and temporal structure prior, so
Yeah.
you can get a better result?
Yeah, absolutely. These are great questions, and actually, it's a time when I should advertise the work of other groups that have picked up on these on exactly the things you've raised here. So you're right. What I showed you was just using regularized maximum likelihood estimation. I could call it map estimation with a prior based on just a low TV norm or something like that. So we didn't try to incorporate more sophisticated priors, but Gordon Wetstein's group at Stanford has really, I would say they were most inspired by Josh Rapp's work on withstanding a lot of ambient light. So they took our data and tried to reprocess with some deep learning based methods, and they get good results. They're not way better than our results. Actually, it's very interesting to see the comparisons, because they get better results than we get at lower noise levels, but at the higher noise levels, their trained methods don't do better than our methods. But it's certainly an interesting approach for sure. And I should also mention at Heriot-Watt University, There's a group of Johan Altman and Steve McLaughlin. They've also picked up on this stuff very strongly, and they incorporate much more interesting priors and use MCMC methods to sample from posteriors, and they form way better multi-layer reconstructions than we form. So the kind of reconstruction that I showed you here, they've done some things much more sophisticated than this. Very nice work. In this work, actually, we do only a pixel by pixel reconstruction. We don't even exploit any spatial correlation because, I don't know, we just couldn't think of how to do it very computationally efficiently at the time. That's really nice work out of that Harriet Walk group. And I know of other work, priors that that exploit correlation between depth and reflectivity. There was a nice work by Ivana Tosic and some of her collaborators on that at some point. We've not tried to incorporate that with our measurement models. I think those complicated priors have only really been used with very simple measurement models, and for us the complexity is more on the measurement side. And then I think there was another part of your question that I've forgotten.
How efficient?
Okay, right, the part I wanted to forget. So, you know, I don't know. It's not something that we're especially focused on. We're really kind of just trying to have proof of concept demonstrations, but they're not extraordinarily complicated. I think that, I think for the first photon imaging, you know, maybe it's on the order of a few seconds per data set. So that's how we're able to do something like, whoops. We can do this kind of evaluation by averaging, you know, computing statistics over large numbers of reconstructions, because each reconstruction is not that computationally intensive.
Okay. Any other question? No further question. That's something else to do.
All right. Thank you.